So here comes the good, bad, and the ugly. I'm not sure which one you are. Or sorry about
I'm
that.
I'm the Australian.
So, now we have the great pleasure to listen to Professor Arnold Pears, who recently moved to KTH. So I guess another local Australian
product.
Yeah. Go ahead.
Thank you very much, Fredrik. Yep. So, I'm going to try and make this fairly brief, and I've got fewer slides than Matti, but I'm going to refer to him in the first one pretty much. So I'm Arnold Piers. I began as a computer scientist, and I've worked as a computer scientist for the last nearly 30 years in computer architecture and computer networks, etc., 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 etc. So much of what Matti said, I sort of recognise. Over the last 10 or so years, I've made a transition into being much more interested in how the learning process works, and I'm now a Professor of Engineering Education at KTH. So when I say the good, the bad, and the ugly, what do I mean? Well, there are some good things that we can draw out of all of this experience over, well, is it several hundred years or is it several thousand years of computing in different forms? And as Matti said, part of the original goal was to distribute computation and to eliminate the human factor. We've done that pretty successfully in a large number of areas. But we should remember that, as Matti said himself, computing is much more than just programming. There is just so much more there that is actually much more interesting than programming. And some of the types of thinking can be developed at early age. And I'm going to give you some examples of that in some of the next slides. Creativity is one of the keystones of this. If we can't get people enthused and help them to be creative through these types of new skills, I think we've failed. And I don't think people will embrace it either. Young people particularly are not interested in being bored, especially not with YouTube, right? So if you're going to compete with YouTube and Minecraft and so forth, well, you better get your act together. How do we learn stuff? I think we all learn stuff by making mistakes. And students need space to explore, to make mistakes, to go where nobody's gone before and to get it wrong. By doing that, you learn something and you hone your skills and you don't make the same mistake the next time. And so those types of open, free environments are something that we should all really try to look at in our classrooms. And as you'll notice in these slides, for every point I've put a reference. So you could go away and you can read some of that literature if you want to know where I got that idea from. And remember, you don't need a computer, right? A lot of these ways of thinking, a lot of these ideas require no computer. They require a bunch of friends in a room and some props. And I can teach 12-year-olds to do bubble sort, and I can demonstrate computer networking principles. There's a lot of stuff you can do, and there are a lot of resources out there. Go away and look at Tim Bell's website. By the way, Jeanette, you missed New Zealand. They also have a national curriculum for computing. And you, my friend Valentina Dojeni in Lithuania, she also has been really pioneering with this Bebras Beaver Challenge, which I'm sure many of you are familiar with. And they're also, while we can talk about what those exercises represent and what types of computational thinking the people who've created those exercises think are embodied into them. And there's a bit of research to be done there, actually, because you've got this massive database of what people think computational thinking is, experts of all different sorts. That we should data mine, we should do a bit of smart analysis and try and work out what patterns are there in that data, because that's what our discipline thinks computational thinking is about, at least in part. So what does good look like? Well, we'll see if I can make this play. I don't know how we do that. Oh, look, there you go. So this is creativity at work.
We have a robot, and that one will be that it should pick up the red object, store it, then the yellow object and store it, and then a red object again and store it, and then take another turn by just not storing anything. And then we want to demonstrate the same program again, but we will do a manual override, so it will go in the order red, red, yellow.
Okay. And the red should be stored here, right?
Yeah,
and the yellow over there.
Yeah, currently both of the reds should be stored at that shelf and the yellow at that shelf. So what I will do is to start the Java application and then send the code to the robot. Show it 2 times.
Yeah. See, now we can see failure happening. So this is a
Yeah.
project group of students in
It takes a
4th
while
year in
before
computer
it
science.
actually starts, and you can see the live video feed there, and the temperature from the Arduino should update as the robot goes.
All right. Maybe we'll try and move on. Okay, here's another view. This is what good looks like. Look at those young, happy faces, right? They're people who achieved something, really achieved something. And I was amazed when I saw this. Look at this just for a second, and then realize that there are 2 more inputs here. You hang on to this, and then this is programmed to play a tune as you press on the paper clips or dip your fingers in the 2 cups, right? So those 2 young ladies have devised that, yes, built on some pre-made components. And we were just asked the question earlier, was it possible for people at an early age to think algorithmically? Well, look at this. They invented their own notation in order to be able to play the music reliably. So they needed to eliminate the necessity to memorize complex patterns. They devised their own notation. So the arrows represent the paper clips and the direction of the paper clip. The round things are the buckets, and they have 2 different buckets, and they had different signs on them, so you knew which little cup to put your finger in. And then they needed to invent a notation to play chords. So they have an extra notation in there. I'll let you see if you can work that one out, which allows them to work out when they should play things simultaneously. And in fact, they do it by overlapping symbols on top of each other, or drawing a double symbol. Now, I would claim that this is an outstanding demonstration of 2 people who have constructed an artifact, learned to program it, have devised their own language in order to describe their own algorithm in a way that eliminates human error. Right? So yes, it's possible to develop those skills. I was amazed when I walked into that classroom in Halmstad, and these 2 young ladies were sitting there in the classroom, and they had more or less done this on their own. They could describe to me exactly how they'd done it. So I don't think that we're being over-ambitious. That's what I'm trying to say here. I think there are many, many good things that can be done. They can be done with very simple tools. And computational thinking is something that is intuitive. People would like to describe their environment in unambiguous ways. They would like to communicate intention to other people. That's what we do with language. Now, language is not very good at it, actually, because what I say and what you hear are not really the same thing. And I won't make a comment on automatic translation, because I learned a lot about Swedish culture by learning the Swedish language, so I'm not sure I'm in favour of automated translation. We'll move on. So I should have put in more Wild Western pictures. I needed a Clint Eastwood picture here. But you'll have to just go with the text. So, you know, we can do this really badly. We can focus on artifacts and technology and decontextualize them. And we know that that has some really nasty side effects. It can have an extremely off-putting impact on young women, for instance, not to mention other perhaps disempowered or marginalised groups in different cultural settings. One of the things that we do a lot at universities, and maybe it occurs less in the school system, is that we get students to solve the teacher's problem, a problem that I think is interesting. So let's all write a program to implement the first 37 numbers in the Fibonacci sequence. And that's a problem that nobody cares about, not even me, actually. But it's very common. You know, it's in all computer science textbooks when I was a student. You know, that was one of the first exercises. If it wasn't to draw a triangle on the screen using asterisks or something else like that that was equally annoying and trivial. We didn't contextualize. You know, young people today don't want to solve abstract, complex mathematical problems. They don't see the point of computing as being to solve computational challenges anymore. It's not about computing missile trajectories. It's not about solving the navigational tables. It's not about computing tables of logarithms to 57 decimal places. It's about solving society's problems and environmental challenges and other things. We need to contextualize. So we can do this really badly by getting our heads around it the wrong way. We can also send some very strong negative messages through the way that we communicate. How inclusive are we really? You know, people have been studying this for quite a while, and we know that there are ways of communicating in the classroom that will turn off more than half the students pretty much instantly. I think for me, as a person interested in learning theory, the one that's most one of the ones that most disturbs me is the perhaps apocryphal story of the MIT, or was it Stanford, professor who fronted up to the first year class. Right, this is a very, very difficult course, and all of you should really put your noses to the grindstone and get into it. Look to your left and look to your right. Only one of you will be here in 6 months' time. Right? I mean, well, that was an encouraging and enthusing message, wasn't it? You know, you just programmed half of your class to drop out. Well, that was, you know, but of course, you know, what he was trying to do was say, this is tough, you need to put your back into it, please be highly motivated. But the way of conveying that message wasn't perhaps quite appropriate to what he wanted to achieve. So communication climate and inclusiveness is key. We really need more diversity, especially in computing, and in much of engineering also. And there's a lot of organisational research literature that tells us that high quality decisions are best achieved in diverse constellations, because you illuminate more viewpoints on any given problem, right? You don't want a bunch of guys in three-piece suits sitting around a board meeting sort of, well, we've had a recent example of that in Sweden, haven't we, measuring their penises. But anyway, we can also get it wrong by focusing too much on the syntax rather than the problem, right? Did those girls need to learn any syntax in order to achieve that? Very, very little. Did they learn a lot about computing and how to represent algorithms and how to structure thinking? Yes, indeed. So getting buried in the details of a complex programming language, possibly not the best way to go. We can get that wrong too. Doesn't mean that Scratch is the answer to everything either. I'm very much in Matty's camp. There's no really true, correct, one-size-fits-all solution to any of these problems. But when you go into the classroom, or when you're thinking about a new initiative in education, we need to take these things into account and bring these different perspectives into the discussion, because otherwise I think we run the risk of missing something. So what looks really ugly in this? You know, this is where I needed another picture, but you're not going to get one. I think the nastiest thing I have ever experienced in my 30 years as an academic is this, the language wars. Right? Computer scientists can spend an entire week, months, years arguing about what is the best language with which to teach introductory programming, as though it was all about programming. So we fall into our own trap. First we say, oh, computing is much more than programming, and then we sit in a boardroom for 27 hours with people slamming their fist on the table saying, it has to be Python. My gut feeling says it has to be C++. We have to be relevant to industry. It has to be Java. They're competing perspectives on the world, and nobody's actually right or wrong, really. But we need to ask ourselves, was that well invested effort? You know, maybe we should all sit down and have a think, a long, serious think, as Matti said. What's our basis? What's our foundation here? What things do we really think? And Jeanette brought this up this morning. What does everybody need to know? What is the computational thinking general knowledge that we expect every person to have when they finish primary school, when they finish high school, when they finish gymnasium, when they finish university. You know, we know what that is for biology, and chemistry and mathematics. We've nutted that out over hundreds of years, and everybody has reached some type of consensus about, yeah, what do we really want to achieve in terms of fundamental concept knowledge and a little bit of intuition about our biological systems, mathematics, blah, blah, blah. We don't have that for computing. We need to really sit down and have a think. Now my chairman is telling me I have 1 minute, so I have one more point. Folk pedagogy. A lot of us have very strong beliefs about how you should teach and not much empirical evidence to back them up. We need to have a much broader discussion about what are the suitable pedagogies? How do we implement teaching at different levels? How can we follow this up, investigate it, understand it? And I hope that that's what I'm going to spend quite a bit of my career at KTH doing. Thank you very much for your attention.
Thank you, Arnold. So give it to Susan. So, quick question to Arnold while we're changing speakers. Or, oh yes, but
Yes, what is the relationship? Sorry. I was curious about the relationship between systems in general. For the example, system science and systems thinking. Nobody seems to be talking about that, but we have some experience with that as providing a basis for even learning later about computational thinking, because there is a strong relationship.
There is indeed, and perhaps it was remiss of me as a computer scientist to sort of step too much into my own discipline. You're of course very correct. Let's go back to Matti's claim in the first talk, though. You know, this is a chicken and the egg scenario. If you read Palumbo's article on problem solving, he's used, he investigates how programming languages and systems thinking are used to learn how programming and systems thinking is used to solve different types of problem solving skills, to implement problem solving skills and their development. So we need to have a think about, do the problems come first? Does the programming come first? Is it the programming that generates, or the systems thinking that generates the computational thinking, or the other way around? And as Matti says, I don't think we know that. I think we know how we developed it. We developed it by going from programming to problem solving, because the problem solving and the computational thinking were the result of the formalisms that we were taught and the incremental building on bigger and bigger and more complex problems. And when you talk about systems thinking, it's the same sort of idea, that you have these basic concepts and you build something much more complex. But I think we need to really understand that. It wasn't an easy answer, I'm afraid. We just don't know is basically the answer.